Thanks. Thanks for the invitation, first of all. Okay, yeah. I'm already seeing it in front of my eyes, but I think you can just leave it there because I usually go over time. Yeah. So yeah, thanks for the invitation. So I will maybe skip a few slides because I was also not very good on the timing. I'm not good on the timing usually. So I will talk about embedded STT-MRAM. So I will cover like 4 major parts. So maybe, first of all, building trust in this new technology, and then how we move ahead and even beyond with spintronics in GlobalFoundries. So just as a broad overview, I always show this. So this is the embedded memory market, in my very simple view, right? We have this main contender, the flash, of course, the main workhorse still. We didn't see it in the Müller report. I mean, talking just about embedded memories, but there will be a long-lasting legacy still of embedded flash in a lot of markets before the others take over entirely. The other front-end memory is the FFET, and then there's this very exotic FRAM. We don't know where to really put it. And then there's this 4, I say, major MIM capacitors in the back end of line, which modulate the resistance, like the FTJ, the MRAM, the spin valve, and the resistive RAM with the filaments, and of course the phase change memory we heard about. So the benefit in terms of, from integration point of view of all of them is that it's easier to implement something in the back end. It's easier portable from node to node than one of these front-end memories. They have their advantage, but it becomes more and more difficult to port them to FinFET, gate-all-around, because their usual transistor flavor is still like polysilicon-like, not high-k metal gate, not FinFET, not gate-all-around, right? So they will always be a very special entity in the front end of line. That's why these back end of line memories are very attractive. It's not super easy to port them to the next node, but it's way more easy than to port them to a new technology node than compared to a front end of line memory. So at GlobalFoundries, we are looking at quite a lot of them. We have, of course, our eFlash offering. We have some significant research in ferroelectric transistors as well as in FRAM, but we are not in a pre-production development stage with those yet. Our main first emerging memory that we implemented is the MRAM. So we have it on consumer industrial on 22 FDX. We develop it for automotive. We are in the final stage for 22, and we are directly going to automotive on 12 nanometer FinFET. We also have some research activity on SOT. And of course, in parallel, we are like all the other major foundries are developing resistive RAM, first for 22 and then also for 12. Why do we still think MRAM is the main contender? And I don't share the prediction of Müller, to be honest. I think the market penetration of RRAM into automotive will be way slower than maybe a lot of people anticipate. The reason is the trust, right? There's not much of this technology out there, and in the end, automotive customers will remain conservative, and they want to see field-proven technologies, and MRAM has a key advantage there. In our opinion, and it's still for us the #1 flash contender since it has a scalability roadmap beyond 2x nanometer node. It has proven that it can reach the sub-ppm level maturity level that is required for DPPM level automotive requirements. It has the field-proven solder reflow capability, meaning data retention after chip soldering. And what we offer as a bonus to our customers is definitely higher write speed, higher than any other memory in the industry can provide. And this comes especially important for all these fast over-the-air updates, right? So maybe in the past, you had cars that updated maybe all 3 years when they were in the repair shop. But there are situations now that Teslas or something, they can update daily. So this becomes an issue, right? So these new codes are frequently put into the car. So a very fast turnaround time of this over-the-air update is key. we can offer higher endurance than any other memory around there. So that means designers have the possibility to not only do code storage, but also use portions of the memory for data logging. For our automotive application, for example, we are offering big code macros, and with the same flavor, we offer small data macros, which offer much, much higher endurance cycling, so sensor data logging, and things like that. No other memory at the moment can offer this, going into the 500K or 1 million cycles of endurance. And of course, comparing to Flash, we offer lower mask adder, and that results in lower cost for the customer. So our first implementation has been the consumer MRAM, as I said, so it's a very classical implementation. So we have it in the back end of line. So the transistors in the front end are standard 22 FDX transistors. So here you can see a cross-section. So all of this also from our other contenders, none of this is very confidential anymore since we have been reverse engineered multiple times now. So this is the outline of my talk. So I would like to say, how do we build trust? So I will quickly go through some line of defense for volume manufacturing, which is very unique in MRAM. Then about only a few words about magnetic immunity. I think this is maybe something that is discussed so roughly this year already. Moving ahead, I would like to show our automotive readiness, and then I would like to show like a little thing, just some very recent data if I come to that, which is very surprising what we have in a research collaboration with a French, Dutch, German, European project where we were able to detect some 3 magnon scattering with our MTJs with a reservoir computing approach. Okay, not to lose any time. So line of defense. Line of defense for us is protecting our customers, of course, in the first place from any reliability concern in the life of the chip. But for us, it has a different meaning because we need to protect ourselves from manufacturing wafers that are in the end scrap, right? We need to detect misprocessing as early as possible, so don't drive this wafer out, see at the wafer electrical test at the end that this wafer is actually scrap. That means we lose a lot of money. So there's always, we differentiate between defectivity and parametric. Defectivity is very simple, right? There's a particle, it shorts a line, wafer is dead, right? Parametric in MRAM is similar like in other memories. It's parametric means that if, for example, for some reason that the mean of the write voltage is too high, we cannot drive in our macros this kind of write voltage. So we will have a parametric loss by write error rate or by data retention loss or things like that. So these are the two differences. If I would be a standalone company, it would be super easy for me because I see everything at wafer product level sort. I do all my reliability checks. I can see the full yield map. You can see the small dies which are fail. It's a very small GPS sensor chip, so you have a very fine resolution of our MRAM where it is fail and where not, because there has been some arcing at the, that's a bad example, right? So there has been some arcing and stuff, I can see what is fail. But we are foundry, meaning we ship the wafer, so all we have is the wafer electrical test on the scribe lines to judge if the wafer is good or not, right? So that is basically the challenge of being a foundry. So we cannot do this, so we need to rely on defect inspection and on some very smart scribe line tests to predict actually the outcome. So this is also something that is in a sense unique in MRAM. So the scribe line testing electrically, we drive magnetic fields and we measure the RH loop, so the magnetically driven hysteresis as well as the current driven hysteresis of the device you can see on the right side. So this helps us actually to predict data retention, magnetic immunity, read margin, write margin, and cycling endurance and things like that on a parametric base, right? We are only looking at means of wafers, or let's say wafer maps. So we can only predict parametric yield loss by that. For defectivity, it's very classical, like in any other technology, right? There's nothing new. We do, of course, do defect inspection, optically, bright field, dark field inspections to see particles, and our yield engineers are then seeing if these particles are really killer defects. So this is the basically killer defects per wafer. So not every particle has the same kill rate for the IP like other particles. And then we are just doing it very regularly like in any other technology. But relying on this wafer electrical test is way too late for us, right? I don't want to see if I'm manufacturing wafers and I'm having an issue in my MRAM zone, And I'm driving all this material out, and at wafer electrical test, before I ship to customer, I see this wafer as scrap. I have all this material at risk because I don't know, was this a persistent issue in the MTJ tool or was it a one-time event, right? So we would lose a lot of material. So what we do in MRAM in addition is we always run a full MTJ stack wafer in parallel. So we are basically monitoring our MTJ stack on blanket wafers, and luckily, because of hard disk drive industry and all these significant and amazing work that has been done on magnetics, we have very versatile equipment that can tell us exactly what to expect from our wafers at fab out if we just look at the blanket stack, because we can, oh my God. Okay, so, but even that is not enough for us, so we are worked very closely with KLA to make an inline detection directly on product level. So we're having a very strong line of defense using directly on product. We measure the TMR, the resistance area product, the HK, as well as the SAF, so the synthetic antiferromagnet properties directly on the wafer. So, and I'm not going into the line of defense 2 and 3. They are standard, and line of defense 4 is package level reliability. But this is very unique to MRAM that we can directly at the core measure the magnetic properties and predict the fab out result, right? None of the other memories have that in that sophisticated way. I will skip the magnetic immunity because I think this, I'm just tired of talking about it. I mean, there's a very nice paper from Bernard coming out with some of our GF authors. Look into that. I think there's a lot of misconception, and it needs to be viewed realistically, right? And especially the automotive sector is a space where you can very readily predict the position of your MCU. You know where it's gonna go, you know the distances, you know the systematic exposure to magnetic fields. So if at all, this is the perfect implementation spot to get the field experience and to see this kind of magnetic immunity not being a concern, right? I agree that in some consumer markets, especially in the very low budget, like companies that sell chips online, they have 100,000 end customers with 100,000 different little smartwatches or something. Yes, then it is maybe a big effort to always think about systematic field exposure. But the MCU market in automotive is something very different, and I don't see a magnetic immunity concern there. To the automotive sector in general. So I always show this. This is an outdated picture already, but the code in a car is actually the code lines in a car is exceptionally high. It's more than the Facebook source code. It's more than, it's an old thing. It's Windows Vista, but still, I think if you would compare it now, you would see that the lines of codes in a car, in a modern software-defined vehicle, are like insanely high. So it's a perfect marketplace for embedded memory, right? So like I said, fast over-the-air update is key, and fail and secure operation, and a real-time access, because you need to operate at the edge. You cannot send information into the cloud to ask if this is maybe a pedestrian or not. The car needs to brake immediately, right? So it's a lot of very fast edge computing required. I think I will still skip this due to time reasons. This is just to illustrate you that the PPM requirements are very, very strong for automotive, since they want this chip failure rate below 1 dppm. So meaning if we want to achieve that and have a 2-bit ECC error correction, we have to achieve end of life. So not only D0 yield, end of life, or after all reliability items combined, we have to achieve this 1 ppm end of life to really have a correctable arrow still at the end of life, which means this is a stringent requirement that is very hard to achieve for other memories. The main challenge actually in automotive is we have, of course, this classical time voltage dilemma like for any other kind of memory. In MRAM, it has a special name, the STT efficiency. So between the speed, the right voltage, and the retention. But we have that under control. Even in our consumer industrial technology, we can show that we can cycle over 1 million. We have very strong data retention, so solder reflow is no issue for us. 150C data retention is also no issue, because if you can make solder reflow, you can make it everywhere. So that's basically how you can say it, because the temperature coefficient in MRAM is so steep. If you can survive 260 C, you have basically thousands of years retention in a normal use case scenario, which is not with respect to the solder reflow. But in automotive, key for MRAM, or the big challenge that we had to overcome was read margin. So we have a 78% TMR drop from going to -40 to the 150 C read scenario. So we overcame this issue. You can see we made retention better, we made write margin better. I will skip this, but you can see we also fixed the read margin. Here you can see 150 C sense amp margin. So you can imagine this, the width of this green curve basically tells you how easy it is for the sense amp to see 1 and 0 at 150 C. You can see compared to our consumer industrial stack, we significantly improved our read margin, and we can easily read megabit macros with 0 fail at 150 C. So this was our main challenge, which was overcome. Moving ahead, we are going to FinFET technology. Can I talk a little bit into the coffee break, or should I stop? I need maybe 5 more minutes. Oh, okay. So, okay, I will be very brief. So the main thing for us, with FinFET, we don't have the front end of line limitation to cell size anymore, because we can drive a lot with the FinFET. So we can actually offer 50% area gain going to FinFET also on the MRAM macro. The key challenge is not only think about lateral scaling, also think about vertical scaling. The problem is everything gets smaller. It's not only the footprint you see from above, it's especially the vertical height. And this is a big challenge for MRAM, because MRAM, in the classical implementation here, I wanted to tell you a little story about our integration learning in the past. But in the end, we came out at this very weird mushroom-like thing, right? The reason is because we have that cleaning process on the sidewall, and we always have some over-edge margin on the side. So we need that little stamp underneath the MRAM pillar to really gouge enough into the silicon to clean the sidewall so that we don't have any partial shorts. So going to technology that has a much denser pitch, like the forest gets much more dense, so less light comes into the forest. So we have a problem cleaning that sidewall, right? And in addition, we have a problem scaling vertically. So this is the major challenge we are overcoming right now, to make basically MTJ capable for FinFET technology. That's what our competitors do as well. It is possible, I can tell you, this roadblock can be resolved. So there will be, you will see technologies coming out at 12 LP plus. You will see them at 60 nanometer FinFET from TSMC. There will be Samsung publications showing 8 nanometer at IEDM. So you will see that scaling is possible for MRAM. You will not see a similar thing for other memories in the next time. And then just because it's such a nice result, and I want to disseminate a little bit of the European project we do together. Like I said, it's a French, German, Dutch collaboration. So it's a very fancy idea, actually, and I was the one who's actually saying it's not gonna work, but it's a reservoir computing. Basically, a reservoir computing means it's like for AI application, but a reservoir has like all this, you can imagine, it has all these pre-trained weights inside. You cannot really influence. It's really deep. You send something in, it gives you something out, which you just train the output. And this magnetic disks, they react very specifically to RF signals because they excite magnons. And this 3 magnon scattering is very non-linear. And if you put 2 input signal outs, there will always be a distinct response of your reservoir in terms of the pattern it will create in reciprocal space, which you can then, in the ideal case, detect with an MTJ which is underneath. So we took we modified our MTJ, so we ran some wafers for HZDR, where we modified our MTJ to be more sensor-like. We made the HK very weak, so we made it very fluffy in a way. So, and then our partner put an RF antenna on top, put the different input signals in, and this is a Brilliant light scattering microscopy, where you can see that you can see the magnon mode splitting off, and now we detected it with our MTJ underneath. And you can see that we have a very, very narrow line width. It's much better than actually this microscopy technique because the network analyzer can pick up much more precise line width. So this is just a very early stage, but it actually proves that it is possible to use the magnetic, our magnetic sense head as a detector for this reservoir. And in the end, the vision is that we have a lot of these, right? We have thousands of bits. We could actually map the entire disk with our MTJs. So we could make like a CCD camera kind of picture of these reservoirs. So this is the holy grail to see. But it was a very nice collaboration. And I just included this to show that there is also life beyond STT-MRAM or ideas that work. And I think the nice thing about, I worked on all memories I showed before in my life. MRAM is the most predictable. You do something, you have an idea, and in 60% of the cases it works. Because it is predictable, it follows a physics that we understand to a great extent. I never had that feeling with the other memories, to be honest, right? There you have an idea and the opposite happens. So that's my talking for Spintronics here. That's the great benefit I see in MRAM, that it is very predictable in its core nature. Yeah, thanks, and sorry for overstepping.